In the world of high-end filmmaking, every frame depends on a masterpiece of engineering hidden at the front of the camera, the cinema lens. Unlike standard photography lenses, these optical titans are designed for absolute consistency. They must maintain sharpness from edge to edge, eliminate distorted colors, and provide a perfectly smooth focus pull that never shifts the image. A single set of cinema primes can cost more than a luxury sports car, and for good reason. They are the result of thousands of hours of precision labor, and it all starts with the physics of light. Within these metal housings, light must be bent, filtered, and focused with a tolerance thinner than a human hair. Every ray of light must strike the sensor at the exact same microsecond, or the immersion is broken. To achieve this, engineers must master the most stubborn material on Earth, glass. We aren't just talking about windows, we are talking about ultra-pure optical crystals forged in the heat of a furnace and ground to nanometer precision. This is the story of how raw sand and rare earth elements are transformed into the eyes of Hollywood. The blueprint of visual storytelling begins with the grind.
The journey begins not in a factory, but in a lab. Standard glass is full of microscopic imperfections that would ruin a 4K image. For cinema lenses, manufacturers use specialized optical glass enriched with rare earth elements like lanthanum or niobium. These additives change how the glass bends light, a property known as the refractive index. The process starts by melting these raw powders at temperatures exceeding 2,500 degrees Fahrenheit into a glowing, molten liquid. This liquid is stirred constantly to ensure a perfectly homogeneous mixture. Any tiny bubble or impurity would act like a black hole in the final image. Once the mixture is purified, it's poured into molds to create blanks, thick, opaque discs of glass that look nothing like a lens yet. These blanks undergo a process called annealing. They are cooled down incredibly slowly, sometimes over the course of several weeks. This controlled cooling prevents internal stress from building up, which could cause the glass to crack or warp during the high-pressure grinding stages later on. What remains is a block of glass so pure, it is essentially invisible to the light passing through it.
Now, the brute force of engineering meets the fragility of glass. The cooled blanks enter the generating stage. This is where the lens gets its primary shape. Using industrial-grade diamond-tipped grinding wheels spinning at thousands of RPM, the machines begin to shave away the excess material. It is a violent but calculated process. High-pressure streams of coolant flood the glass to prevent the intense friction from shattering the blank. The machines follow a digital blueprint to create either a convex curve, which bulges outward to converge light, or a concave curve, which dips inward to diverge it. At this stage, the surface is no longer transparent. It looks like frosted ice. Its texture is rough to the touch, covered in microscopic pits left behind by the diamonds, but the geometry must already be nearly perfect. Even at this early step, the curve is accurate to within 20 micrometers. For context, a standard piece of paper is about 100 micrometers thick. The lens is taking shape, but it is still blind. To see through it, we must go deeper into the polishing phase.
As the lens moves to the lapping station, the grit gets smaller. The goal is to smooth out the diamond scars from the previous step. We use a series of finer and finer abrasive slurries, mixtures of water and aluminum oxide or silicon carbide. The lens is placed against a lap, a tool that perfectly matches the desired curvature. As the tool oscillates and rotates in a complex dance, the slurry acts like liquid sandpaper. This is a game of patience and friction. The precision moves from the world of millimeters to the world of microns. Every few minutes, the process is paused and the lens is measured using a spherometer. This device checks the curvature at multiple points to ensure the lens isn't becoming lopsided. For cinema optics, being close isn't enough. If the curve is off by even a fraction of a percent, the lens will suffer from spherical aberration, causing the image to look soft or hazy. It takes hours of constant friction to reach the level of smoothness required for the next critical phase, polishing.
This is where the magic happens. The lens is still translucent, but in the polishing stage, it finally becomes clear. Instead of metal tools, we use soft pads made of polyurethane or pitch, and a special polishing compound called cerium oxide. Cerium oxide doesn't just scratch the surface, it reacts chemically with the glass on a molecular level to level out the tiny peaks and valleys. This process is incredibly delicate. The temperature of the room is strictly controlled to within 1 degree because heat causes glass to expand, and even a tiny expansion would ruin the measurement. We are now working at the scale of nanometers. To verify the surface, engineers use a laser interferometer. This device bounces a laser off the lens and compares it to a master reference. If the two waves of light don't match, it creates an interference pattern that looks like topographical map lines.
The technicians adjust the machines until those lines are perfectly straight, meaning the surface is accurate to within 1/20th the wavelength of light. At this point, the glass is so smooth that if it were the size of a football field, the highest bump would be smaller than a grain of sand. In modern cinema, we often need aspheric lenses. Typical lenses are parts of a sphere, but these have complex non-spherical shapes that allow a simple piece of glass to do the work of three. Mastering the asphere is the black belt level of lens making. Because the curve changes as you move away from the center, standard rotating tools don't work. Instead, we use computer numerical control, or CNC, grinding. A small high-speed tool traces the exact profile of the lens bit by bit. This is followed by magnetorheological finishing, or MRF. This futuristic process uses a magnetic fluid loaded with abrasives. By changing the magnetic field, engineers can precisely control how much glass is removed from specific tiny spots on the lens. This allows for sub-wavelength corrections. The result is a lens element that can correct for distortions that have plagued photographers for over a century. It's the reason a modern cinema lens can be both wide-angle and perfectly rectilinear, with no fisheye stretching at the corners. This precision is what separates a cheap lens from a cinematic masterpiece. Even a perfect piece of glass is useless if it isn't perfectly centered. The optical axis, the exact center of the curve, must align perfectly with the physical center of the lens element. If it's tilted by even a fraction of a degree, the image will be sharp on one side and blurry on the other. To fix this, we use a process called centering. The lens is attached to a high-speed spindle using a vacuum. A laser beam is shot through the lens as it spins. If the lens is off-center, the laser spot will wobble on the sensor. A technician, or a high-precision robot, adjusts the lens until the laser remains perfectly still. Once centered, a diamond grinding wheel comes in and shaves the outer edges of the glass until the lens is perfectly circular and the diameter is exact to within microns. The edges are then painted with a special matte black ink. This prevents light from reflecting off the sides of the glass inside the lens barrel, ensuring that the flare and ghosting are kept under strict control. Now, the glass is ready for its final armor, the coating. If you look at a cinema lens, you'll see beautiful reflections of purple, green, and amber. These aren't just for show. Untreated glass reflects about 4% of the light that hits it. In a lens with 20 elements, that would mean almost half the light would be lost before it hits the sensor. To solve this, the glass enters a vacuum deposition chamber. Inside this airless void, rare minerals like magnesium fluoride are heated with an electron beam until they vaporize. The vaporized molecules rise and bond to the surface of the lens in layers only a few nanometers thick. We're talking about layers roughly 500 atoms deep. Each layer is designed to cancel out specific wavelengths of light through destructive interference. This reduces reflections to less than 0.1% and increases light transmission to nearly 100%. These coatings are what give a lens its character, the way it handles flares and color. It's high-stakes chemistry performed in a vacuum, and it's the final step before the glass is wedded to the machine. While the glass is the eye, the barrel is the muscle. A cinema lens must be built like a tank. The internal housing is usually made from aerospace-grade aluminum or titanium. Unlike a plastic consumer lens, every moving part here is metal on metal. This is the assembly of the cam system. Inside the barrel, complex helicoid gears are machined with extreme tolerances. When a cinematographer turns the focus ring, these gears move multiple groups of glass elements simultaneously in a synchronized dance. There can be no play or backlash in the movement. Additionally, cinema lenses feature an iris, the aperture, made of up to 18 curved steel blades. These blades must open and close with perfect circularity to create that creamy, out-of-focus background known as bokeh. Every screw is tensioned by hand, and every gear is lubricated with specialized synthetic grease that won't thin out in the heat of a desert or freeze in the Arctic. This mechanical skeleton ensures that the lens will perform identically on day 1 and day 10,000. The final stage is the moment of truth. Every finished lens is placed on an optical bench. A technician projects a high-resolution grid through the lens onto a wall. They are looking for chromatic aberration, color fringing, and coma. If it's not perfect, the lens is disassembled and re-shimmed. Shims are tiny rings of metal, some as thin as 5 micrometers, used to adjust the distance between the glass and the camera sensor. Once calibrated, the lens undergoes torture testing. It's placed on vibration tables that simulate off-road transport and exposed to extreme temperature swings. We need to know that the focus won't shift when the sun hits the black metal barrel. Only after passing these rigorous checks does the lens receive its serial number. It is now a tool capable of capturing history. From the raw sand of the desert to the most precise glass on the planet, it takes months of engineering to create a single cinema lens. But when that first image appears on the big screen, clear, sharp, and lifelike, the effort is visible in every single pixel. This is the pinnacle of optical engineering.
I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.